So Fermat's theorem, remember, holds if P is prime. However, it doesn't say anything about whether or not it's true for non-primes. And in fact, it also holds for some numbers P that aren't prime. For example, the congruence x to the 560 congruent to 1 mod 561 actually holds for all x where the greatest common divisor of x and 561 is 1, even though 561 itself is not prime. In fact, almost every theorem that's true about primes is also going to be true about some non-primes, with one important exception. That exception goes by the name of Wilson's theorem. P minus 1 factorial plus 1 is congruent to 0 mod P if and only if P is prime. We can prove this as follows. P minus 1 plus 1 is P. Factorialing everything gives us... wait, we can't actually do that. To prove this, let's go in the forward direction. Suppose P is prime. Then by Fermat's lesser theorem, x to the power P minus 1 must be congruent to 1 mod P for all values of x between 1 and P minus 1. So x to the power P minus 1 has P minus 1 distinct roots mod P, namely all of those values. Now consider the product x minus 1, x minus 2, and so on, all the way up to x minus P minus 1. So this also has P minus 1 distinct roots mod P, namely those same values. So now let's consider the difference between those two polynomials. Because x equals 1, 2, 3, and so on up to P minus 1 make both expressions 0 mod P, then this polynomial also has P minus 1 distinct roots, namely, stop me if you've heard this already, x equal to 1, 2, 3, and so on. But the leading term of the first product is going to be x to the power P minus 1. And so those x to the power P minus 1 terms will cancel, and so this expression is a degree P minus 2 polynomial with P minus 1 greater than P minus 2 distinct roots. But Lagrange's theorem says that that can't happen, so this is a contradiction, unless... Well, the only way to avoid a contradiction is for these two polynomials to be identically equal, and for the difference to be identically 0. In other words, the expansion of this product gives us x to P minus 1 for all x, including x equals 0. Now if x equals 0, we get over on the left-hand side, which if we remove those negatives, we have a product of the numbers from 1 to P minus 1 and P minus 1 factors of negative 1, and over on the right-hand side we just get negative 1. Now if P is an odd prime, P minus 1 is even, so negative 1 to the power P minus 1 is going to be 1, and so that gives us... On the other hand, if P is 2, which is a very odd prime, we get the left-hand side. Then we get, which is again equal to negative 1. And consequently, if P is prime, whether it's an odd prime or 2, then P minus 1 factorial is congruent to negative 1 mod P, and so P minus 1 factorial plus 1 is congruent to 0. To go in the other direction, suppose that P minus 1 factorial plus 1 is congruent to 0 mod P. Suppose P is composite. Then it must have some factor d, where d is between 1 and P minus 1. But this factor must be included somewhere in P minus 1 factorial. So d divides P minus 1 factorial. But by assumption, p minus 1 factorial plus 1 is congruent to 0 mod p, so that means p has to divide p minus 1 factorial plus 1. And since d divides p, then d also divides this expression. But since d divides p minus 1 factorial, it has to divide 1, which is impossible. Consequently, p can't be composite. So the congruence is true only for primes. So this would seem to give us an infallible way of deciding whether something was prime. So let's try to prove 11 is prime. So to prove 11 is prime, we'll evaluate 11 minus 1, 10 factorial, and we can pair factors that multiply to 12 because that's 1 mod 11. So 4 and 3, those could be replaced with 1. 8 and 7 could be replaced with 1. 9 and 5, and 2 and 6. And so 10 factorial is 10, but mod 11, that's the same as negative 1, and so that proves 11 is prime. Now, Wilson's theorem is not actually a practical way to decide if a number is prime. However, because it is a theorem that is true for all primes and false for all non-primes, it's useful in other contexts. We'll take a look at those next.